thank you. So, first of all, I would like to thank the organizer to invite me to present this large-scale facility we have at Grenoble, and especially the Shrek experiment. As you can see here, there is numerous contributors, and I should have other names as, for example, Javier Boguete or Sergei Nazarenko or Christos Vasilikos and many others. So I hope they will forgive me for this omission. I will begin my talk to try to convince you that there is no other way than using liquid helium if you want to achieve ultra-high Reynolds number in a closed flow. Then I will show you how the use of the Claude-Bath technique enable us to have in the same flow either normal helium or superfluid helium inside the same installation during the same cooldown and using the same sensor. And I will use some results obtained only with global measurements to show you one of the main results in the Shrek experiment. Then I will say a few words about our ongoing experiment, which consists of 3D visualization, and I will end my talk. So, first of all, how difficult is it to achieve ultra-high Reynolds number? You all know that we have this formula for the Reynolds number, and when we deal to a closed flow at laboratory scale, we can say that the length will be in the order of 1 meter, for example. And if you want to increase the Reynolds number, either you increase the velocity up to a fraction of the sound velocity of the fluid, or you change the fluid to decrease the kinematic viscosity. But when it's come with ultra-high Reynolds number, the main problem is the consumption power. And the consumption power is the function of the third power of the kinematic viscosity. And as you can see on this figure, just imagine you have a facility where you can use 400 watts with liquid helium. If we try just to change the fluid in the same facility, and okay, you want to use the same Reynolds number, and what will be the power consumption? And when you see this, you are convinced that you cannot use other fluid than liquid helium to achieve ultra-high Reynolds number. Indeed, you don't want to use a nuclear plant to supply your installation. That will be the case, for example, for ambient air at room temperature, which more than 1 gigawatt. And even with SF6 at 15 bar, you will use more than 100 kilowatts to supply power, the power consumption inside your scale. So if you deal with closed flow, they will automatically induce some drift in temperature, and you cannot make some steady state measurements. That's why liquid helium is mandatory if you want to achieve ultra-high Reynolds number. So in our lab, second thing is, okay, we want to have ultra-high Reynolds number, but we want also to compare the results we have either in superfluid and normal fluid. So to do this, we will avoid contour flow because it has no contour part in classical fluid. You can just have this with superfluid, and we'll just deal with isothermal flow or inertially driven flow. And also, we'll not use only sensor which is only sensitive to one component. Let's say either to superfluid with attenuation of second sound, as it was told to you this morning, because no contour part in classical fluid. And okay, so I will just take a few minutes to give you some insight of what it is difficult to achieve very high Reynolds number when you are a fluid flow which is just directly connected to a saturated bath. Because when you want to increase the velocity, to increase the Reynolds number, then if you are connected to a saturated bath, you have, because you increase the velocity of the fluid, you have to increase its kinetic energy, so you decrease, at least locally, its pressure. And you can go down or below the saturated pressure, and it will induce cavitation. And you want to avoid this. You don't want to have some bubble or something like this in your flow. So as you can see, for example, which is some special experiment, so we're doing cavitation either in normal liquid or in superfluid, it can exist. And this limits the velocity of the liquid of roughly, let's say, 5 meters per second. And another thing which is even more critical is that the fact that if you want to compare the superfluid and normal helium, the normal liquid helium has a very poor heat conductivity, which means that any heat losses which fall on the wall will induce nuclide boiling. You want to avoid this also. So you have a different solution. One of the solutions is to use hydrostatic pressure to pressurize your installation and to have an installation which is very well insulated to avoid radiation heat. And here, this is a solution taken in the 2P experiment. You can see here Philippe, which is moving his experiment. And in this experiment, we have liquid helium at the bottom and some very fine rods which are connected to the top flanges to avoid conductive heat. And the whole experiment is well insulated with MLI to minimize the heat loss. The other solution is to use not, let's say, hydrostatic pressurization, but to use the Claude-Baff technique. I will detail you after. And just to give you some insight, is we use 2 baths, which are the saturated bath, and another bath, which is just thermally connected to the saturated bath, and you can pressurize this second bath to avoid cavitation or nuclide boiling in normal helium. And this is this solution we are taken for the Claude-Baff, for the Schreck. This is the Schreck experiment, the Claude-Baff techniques. So this solution is mandatory if you want to work above the critical pressure. Critical pressure, which is not the same critical point as Carlo Baranghi told us this morning, which he told you about the lambda line here. But I will tell you about the critical point which any fluid have, which is the fact that above this point you have no way to have 2 phases. Okay, and we want to be able to work above this critical point to avoid any risk of having any bubble in our installation. And this critical point is at 2.2 bars. And if you want to pressurize liquid helium at 2.2 bars, you need at least, if you use hydrostatic pressure, you need a column of liquid which is higher than 100 meters. So it's not possible. So you have to use the so-called Claude-Baff technique. And what is interesting also is as you separate the 2 baths, you can decouple the pressure and the temperature, which means at a constant temperature, you can play with the pressure to adjust the density of the fluid. And you can see afterward that it can be interesting also. So this is just a print screen of our installation, which was working 3 weeks ago with this so-called Claude-Baff technique. We have to test a heat exchanger for the same in the framework of a contract for them for the upgrade of the Large Hadron Collider. And you can see here we have the saturated bath and we have the heat exchanger. And here in yellow, the pressurized subcooled superfluid bath, which is here at roughly 1.8 Kelvin and at 4 bar. Okay, and we just input here 20 watts, and we can see that we have a rise in temperature, which is roughly 10 milli-K, which is quite small. And it seemed very simple like this, but it was not the case because you cannot avoid some connection between this pressurized or subcooled superfluid bath and room temperature, because maybe you want to measure the pressure and you need some capillary because it's more easy to have pressure sensor at room temperature, or you need some connection for safety valve, or just to fill with liquid the bath. And that means that sometimes you will have some connection between this superfluid temperature up to T lambda. And as you know, we have a very efficient heat conductivity in superfluid, which means that if we want to make some delta T inside the superfluid, it will induce a huge power falling, because as you have a large heat conductivity, if you have a non-zero delta T, it will induce power losses. and that was is difficult in these techniques. So just to remind you, this is what is usually used with superfluid. You have just a saturated bath, and we have here the interface, and you have the vapor. We are just pumping the vapor to impose pressure and get the corresponding temperature at the interface, either in liquid or here in the vapor. And then you have the gradient from this temperature at the interface up to room temperature here. And if you use superfluid, you have an isothermal bath here. In case of the Claude bath, then you have the cold source, which is the same as previously, and then connected to it, we have a subcool bath, which can be separated in two parts. An isothermal part here with a heat exchanger connected to the cold source, and coming out from it, some connection where we can have some gradient in temperature from superfluid temperature to T lambda. And it is very difficult because, as I said previously, there is a very big heat conductivity in superfluid. And it was just recently, let's say in 1974, that Gérard Claudet found the solution by just said, okay, we just have to use very small cross section for this heat connection to decrease the power losses. And I just want to pay a special tribute to him, because it was my boss and colleague, and it was retired, and now he died last month. So just to recall you, the heat equation for superfluid, when you have a heat flux which is high enough, so you are in the gutter Melink regime, you can have this equation, which is, for example, for 1D. You have here the heat flux, which is at the power law of 3.4, and which is equally here, you have the temperature difference inside the superfluid, and here the apparent heat conductivity. And of course, in 1D, for example, for a pipe, the heat flux here is nothing else than the power divided by the cross section. And if you integrate this equation, which is quite easy in 1D, you have the power, which is your power losses. You want to be as small as possible. And here the cross section, the length at the power 1 over 3.4, and the integral here of the apparent heat conductivity. You can see here, and it can be tabulated here. And what can be seen here is that, of course, if you this integral, the value of this integral depends of your bath temperature, because you integrate from this bath temperature up to T lambda, and depend on the pressure. But here with this value, which is in standard unit, you can see that it's in the order of 10 to 14, which means that the cross section has to be very, very small if you want to have a small power losses. And that's what is the limitation with using this Claude bath technique, and it's very rare. But we use it extensively in our lab, and we begin for turbulence study with two installations, which was to study passive grid flow, and one is E-grid for helium grid, and the other one was TSF for turbulence superfluid in France. And E-grid was mainly designed by Pancho de Ribarne, and it was used to study the behavior of microsense sensor when you eat them, and we put this microsense sensor inside a superfluid flow. And it will detail this on Thursday morning in the session which is dedicated to Alliance sensors. The second installation was TSF, and we use it to achieve R lambda, which is up to 350, which is almost the biggest R lambda for passive grid flow. And we have also this very nice measurement where we have 3 different velocities, and for each velocity we have 2 curves which represent the results for normal and superfluid. And this is here the spectra of the velocity at different length number for the so you will find here the minus 5 to 4 law, which correspond to the inertial range, the Kolmogorov classical result, and we found that we have exactly the same behavior for superfluid and normal fluid. And now I will made all my talk, let's say, sur the Schreck experiments, and so we decided to apply this Claude-Baff technique to giant von Karman flow. The design was, let's say, at least geometrical design was done by our colleague at Saclay, CA Saclay, because they already have a von Karman flow which they use in water. And so we just try to do the same thing with liquid, normal helium, and superfluid. And so we decided to put all the von Karman cell here inside a saturated bath, completely immersed inside it. And then we decided also to have a room temperature motor here at the point, because we don't want that the inefficiency of the motor can input some heat inside the von Karman cell. And we also want to be able to have flexible room temperature motor, as we want to control them either at constant torque or at constant rotating speed, rotating velocity. And of course, as I told you, there is some. It's a big cryostat here. We have more than 4 meters in height, which means here from that point to the propeller, the distance is higher than 3 or 4 meters, let's say. So we need to have a big rod. And as this rod has to go through vacuum vessel, saturated bath before entering into the von Karman cell, of course, we need to have some pipe around this rod to make it tight. And this means that you need a gap between the rotating rod and the pipe. And as I told you previously, in case of subcooled superfluid, you will have a very big power falling on because of this gap. So we decided to avoid any physical connection and to transmit the torque and the rotating velocity by using external magnetic forces. And we designed our own rotating magnetic feed-through, because this component doesn't exist at cryogenic temperature. And also we design special things for safety issue, because we cannot use here some burst disk, for example, because all the more than 1,000 of liquid helium superfluid will just go outside. It doesn't want to see this. So we use a special dedicated cryogenic safety valve, an homemade one, the same thing that we have a homemade rotating feed-through. And we also design the heat exchanger in between the von Karman cell and the saturated bath. So how it looks like, you have here a photo and the CAO design. And what we can say is that we can control, the parameter control are the rotating speed of rotating frequency of each motor, which can be set separately in the 2 cents of rotation between -2 Hz and +2 Hz. The temperature inside the von Karman cell, which can be set between 1.6 Kelvin to 4 Kelvin, and the pressure we can be set independently in between 1 and 4 bar. And this, for example, if you try to calculate the Reynolds number, in normal helium, it's very easy to calculate the Reynolds number in normal helium, because the viscosity, kinetic viscosity is well known, and we can go in this installation up to 10 to the power 8 for the Reynolds number, which corresponds roughly to air lambda, which is higher than 10,000, which is the highest Reynolds number ever achieved up to today. So this is why I told you about ultra-high Reynolds number. We can see here some different type of propeller we use with all this shape of blade, which has been exactly the same, which has been already tested at Saclay in their von Karman cell, which is running with water. And and here this is okay. This is the heat exchanger with 83 copper tube in parallel. And you can see that we wanted to be as canonical as possible for the von Karman flow. So we have added here an aluminum seal sleeve to have a smooth wall. And we also add some disc plate at the top and at the bottom and the top, sorry, and at the rear part of this disc plate, we have glued a heater, resistive heater, which will be used to calibrate the heat exchange between this Von Karman cell and the saturated bath. And we can see afterward that it's very interesting to have this calibration. And okay, this is a photo. And okay, some components. I already told you about our homemade magnetic rotating feed-through. And we also have then the connection between the bottom of this magnetic rotating feed-through and the propellers. And for example, for the bottom propeller, we have more than 2 meters in height. So we have to take into account the differential contraction during cool down. And to do so, we need to add a double telescopic Cardan shaft. And of course, we have first to get rid of the grease, the lubricating grease, as it will be ice at cryogenic temperature. So we use it inside. Instead of this grease, we use molybdenum disulfide to have a lubrication with a solid component. And we do the same thing for the gearbox. We can see here all the components. We have a photo, and we dismantle, we change the ball bearing, and this is a view of the torque meter. We have one of them which is just running at room temperature, and another one which were customized to work at low temperature. Torque meter are input here and here at room temperature, but under vacuum. So this is a photo of the top propeller. You can see here the blade of the top propeller. And this is the static disc plate with the heater, which is at the rear part. And this plate was also been used as a support for here an arrangement of diode and photodiode, which are been used to illuminate some grooves which are spaced by each degrees. And like this, we can have access to the rotating frequency of the disk. Okay, and this is some detail. Same top propeller, but viewed by from the bottom here. And this is the aluminum sleeve. And here in the middle plane, we have an arrangement of different Orion sensor. We can see here 2 different diode of photodiode, because we have spare parts to measure the rotating frequency. And this is a detail of some Orion sensor here, a micro cantilever and 2 hot wire. I will not enter into detail here because this will be the talk of Philippe and Pancho on Thursday morning. And this is some detail of either some classical radial plate or some fractal plate, which has been used because this was an idea of Christos Vassilikos, and there has been a first test at Saclay, and they found that the fractal plate increased the mixing. So we wanted to see if it's the same, appears at higher Reynolds number, and the mixing is also increased with higher Reynolds number in normal helium, and what's happened in superfluid. So we do this, but unfortunately we found no change either in normal helium or in superfluid. And then I think it was my opinion, but okay, that's maybe the problem was the fact that we just use the fractal shape which has been used at Saclay and multiply by a factor of 4 because Schreck is a scale up of 4 of the experiment at Saclay. And for the integral scale, it seemed quite logical to use this factor of 4. But if we go down to a small scale, you know that the Reynolds number in the Schreck experiment will be 100 times higher than in Saclay. So you know that the ratio of the large scale over the dissipative scale as Reynolds at the power 3 divided by 4. So the smallest scale, common scale, will be much smaller in Schreck than in Saclay, even if the experiment is larger. So to my opinion, we should have increased the detail on this fractal bed. As you see, there is not a lot of different scale. It's quite rough. So that's, for me, explains the fact that we didn't see any change. But okay. Okay, so here this is a view of the calibration of the torque meter. We have the torque meter has been recalibrated either at room temperature using simply some mass which are connected to a level arm, and at static point we made just like this, and we just make some force and measure the moment imposed is measured and gives the torque of the, and we just calibrate this. And they have been also calibrated using the motor, which are in line with the torque meter and with a brake here. So we can impose a rotating frequency with the motor and the torques with the brake. And for the cryogenic torque meter, we also recalibrate them at liquid nitrogen temperature, just putting the torque meter inside a nitrogen liquid bath, just because the Young modulus will change for 10 to 20% when it's cooled down. And at nitrogen temperature, all the differential contraction and this change in Young modulus are done. So we check that. And finally, I want to show you some snapshot which has been taken during the assembly of Shrek. So this is our installation at Grenoble, and we have the facility, which is here. There is a top plate, and we have a special design and the crane. And just to show you that once the installation is complete, then you have more than around, let's say, the 5 ton, which has to be support, which is 5,000 kilograms, which is a huge installation. Here you have the von Karman cell, which is installed now, and they have an indium seal here with different screw. You have to put the right torque on the screw to avoid tie click, and of course this has some flanges, and you can see Yuri Mutskarki from Saclay, which is installing his micro pitot tube, which is here. Our teams, which are technician teams, which are helping us with put the flanges after that, which always here you see Mathieu Gibert, which are installing its second sound attenuation sensor, always technician team, and okay, flanges here just a view you have seen previously. This is just to show. Okay, now this is the bottom propeller, which has to be installed. This is the double telescopic cardan, and after that you have also to use an indium seal and with a lot of screw. And after that we have to connect the double cardan with the gearbox to the bottom propeller, which is right there here. Okay, this is the two gearbox, and always the same trouble with the seal, but it's not trouble, just some work. And then we have to put here, this is the saturated bath, and you have to put this inside this. So because we don't have enough height, we have to make some movement with the installation. So we take the top flanges with the von Karman cell, we dissipate it, and then we have to move this saturated bath, which is, as you see, roughly, let's say, 10 meters in height, which contain more than 2,000 of liquid helium at the end of superfluid, of course, which is not. So okay, we have to put this bath in place. Okay, it's done it, and then we make indium seal at the top, and once again some screw, and we put it then the von Karman cell inside this saturated bath, and we have just to put MLI after always indium seal, etc., etc. We put MLI on the saturated bath to avoid any radiation loss. Okay, this is MLI. And then we put all of this inside the vacuum vessel, our cryostat. And this now we have to pump to decrease the pressure up to 10 to minus 6 millibar. And here, this is on the top. Now the physician arrive with all the electronics to control and acquire the acquisition of the data. You can see a lot of guys. This is Mathieu Gibert. There was Christophe Baudet here. There is Yuri Munsiarsi at that side, etc., etc. There is a lot of physicians. There is Philippe Roche was also. I don't see him, but it was there also. And okay, this is the end. And when all is done, we wanted also to verify that our calibration of torque meter was correct. And to do so, we are at room temperature. We pumped a little inside the Van cell in order to have just a low pressure, atmospheric pressure. So the fluid is very low density, and there is no friction, no field friction when you rotate the propeller because the density is so small. And we can just apply the first law of the dynamic, which rely on the, let's say here you have the moment of inertia. We multiply this by the angular acceleration. And this is equal to the external moment applied to this rotating system, right? So this term is negligible because the friction of the fluid is so low. So how we manage? We said, okay, we can have constant acceleration by having our propeller running from, let's say, minus 2 Hertz up to 2 Hertz, or a constant deceleration by going from 2 Hertz to minus 2 Hertz. And we change this rate to change the angular acceleration, right? So for each angular acceleration, we look at the measurement of our torque meter, previously calibrated, and we want to recover the slope, which is the moment of inertia, which has to be 1.7 kilogram per square meter, multiplied per square meter, which is the value given by our software, CAD software, which is SolidWorks, which has been able, of course, to calculate the moment of inertia when you give the density of your, which is alinea, of your propeller, of your rotating element. And we are very nice with this, it's okay. And after that, of course, now I will show you some results. And this is some result obtained with the two propellers which are rotating in exactly the same speed, but either they rotate here in this direction, like this, or here in this direction. And due to the shape of the blade, this configuration like this is more efficient. So for the same, let's say, rotating frequency, you have a lower torque than here with the same rotating frequency in this sense, which is less efficient. So what we do here, we can see that we can say, okay, we can calculate the injected kinetic energy transfer, epsilon, just by multiplying the torque by the rotation frequency and divided by the mass of the fluid, which is in movement. And which is interesting that we here make this measurement for either normal fluid at 2.6 Kelvin or superfluid at 1.63 Kelvin and at 4 bar. That means it's interesting we can play with the density with adjusting the pressure here. And for this condition, we have exactly the same density. So this is the same mass of fluid because the height is the same, okay? And we were able to compare the measurement obtained with superfluid and normal helium, which are exactly the same. Which means that the epsilon injected kinetic energy is the same in superfluid and normal fluid, providing you use the total density for the superfluid. And here we just want to remind you that at 1.63 Kelvin, we have less than 20% of the fluid which is in the normal state. Okay, but we can do also other things. We can use the measurement we have with normal helium, where there is no doubt about how to calculate the Reynolds number because the viscosity, kinematic viscosity is known in classical fluid. And we want to compare the measurements we have in Schreck with the measurements they have in Saclay using some mixture of water and glycol to change the viscosity. At Saclay, and to do this, we need a non-dimensional parameter. We use here Kp as a non-dimensional parameter, and Kp is no more than the non-dimensional epsilon. And this is the same, for example, it can represent the same thing that, for example, the friction coefficient for a pipe, or to the drag coefficient for a sphere, for example. And here you recover, you see, at Saclay they have found the classical laminar law with Kp, which is proportional to the inverse of the Reynolds number. And they have found something which is quite interesting and non-obvious. It was the fact that at Reynolds number, which is in the order of 10 to 4, they found a bifurcation here. That means we can have two results for the same two propellers are here rotating at the same frequency, but here they rotate in this direction, and here or here, and the same thing here, they rotate in this direction. And they found that above Reynolds number up to, let's say, the 10 to 4, we can have either this configuration with two cell flow which connected, each of the cell flow is connected to one propeller with a shear layer in the middle plane, or either just one big cell flow which is connected either to the top propeller or the bottom propeller in a random manner. And with just one big flow, you have a higher torque. And this is some point we have taken to compare exactly Schreck and the von Karman cell at Saclay. This is just the maximum values they have obtained at Saclay with pure water running at the maximum speed for the propeller. And we are able to reduce the same small Reynolds value in Schreck using just room temperature gaseous nitrogen at 4 bar. So we check that our installation is exactly the same in Kp value than those of Saclay. And then we can just add the punch we have in liquid helium. And we found that we still have the same value of the plateau, okay, which means that we didn't find no other bifurcation at higher value of Reynolds number. And we also found no dissipation anomaly at very high Reynolds value. But we also have made other things with this global measurement. We are able to prove, I think it was for the first time, that the injected kinetic energy transfer was equal to the dissipated kinetic energy transfer. Even if it's quite logical, I think that nobody was able to do this before, because it's very difficult to measure the global dissipated kinetic energy, not locally, but a global value. This is, we have to use calorimetric measurements, and you have to do long state measurements. And to do this, you always have some change in external heat losses, for example, room temperature or so. And it's very difficult to have a very high ratio of the signal over noise, right? And in our installation, we have two things which are quite sympathetic, I should say. One is that we have ultra high Reynolds number, which means that this value can be quite high because it's scaled as the third power of the Reynolds number. And secondly, we use the Claude-Debaff techniques. And it's very interesting because normally when you deal with, let's say, cryogenic, you try to measure the dissipated energy by measuring, for example, the vapor flow. But this vapor flow, which arrives in the saturated bath, depend also on the external losses, which means, for example, if the room temperature changes a little, you will change the room radiation, so will change this value. Here, I just recall you that our von Karman cell is completely immersed inside a saturated bath, which means that if you can measure directly the heat exchange in between the von Karman cell and the saturated bath, even if the consumption of the saturated bath change, if you just control the temperature, the von Karman cell will see nothing. And we do this. So how we do this? We just have some, we want to measure the heat transfer in between the von Karman cell and the saturated bath. So the heat flux has to go through 3 resistance in series. You have 2 capital resistance at both sides of the wall, And then you have the resistance, which is due to the resistivity of the wall itself, right? So we calibrate this by using our heater, receiver, which are glued on the rear part of our static disk, right? And we have, of course, thermometers also in each side at the top and the bottom. And we have some thermometer inside the saturated bath also. And we play with the two resistors, top and bottom, and we give also same result. We want to be sure of this because we wanted to be sure that here the bath is isothermal. We do this with propeller at rest, of course, and we are able to have the result of the injected power and the difference in temperature in between this Van Karman cell and the saturated bath. And as the temperature difference is quite small, you see here it is just 20 milli-K. It is what we wanted because we wanted to decrease the temperature as much as possible. So we don't want to have a large difference in temperature. Okay, but with this small difference temperature, we can linearize the curve, and we obtain a coefficient transfer each, which is just dependent on the temperature of the bath, right? So now we are a calibration of the power W and the temperature difference because we have calibrated the heat transfer coefficient. And we do the measurement with now the heater are off, and we just run our propeller. And we just measure the difference temperature and multiply by the heat transfer coefficient, and we can know the dissipated power due to our propeller. And this is what we do. And doing this, I just recall you that here the epsilon, the dissipation, is the power divided by the mass of fluid, which is in movement, right? So I already told you how we measure the kinetic energy transfer, injected kinetic energy transfer. We now measure the kinetic energy dissipation, right? And we do this for the two propellers which are running in that sense, okay? And we do this with just keeping constant the mean value of the speed of the two propellers, which is this mean value, okay, which is maintained constant at 0.45 Hertz, and we change one speed, either the top or the propeller, readjust, and this gives you this theta number. Why we do this? This is because at Saclay, they found that they have in this configuration, in case of a bifurcated regime, just recall it was just one big flow cell, they have some hysteretic curve with two possibilities sometimes for the same value of the theta value. And you wanted to see if this hysterical cycle also exists at ultra-high Reynolds number and if it also exists in superfluid. And we found that, in fact, here we have 1.63 Kelvin. We have this, we recover this, let's say, this hysterical cycle even in superfluid and even at ultra-high Reynolds number. If you want more detail about this, I just invite you to ask Bérangère Dubroul, which has been worked intensively on this with water at Saclay, and she will be there in the next week. And so I will say for the first time we have this equality, and we are very proud of this result. And finally, I would just point out the fact that we are using cryogenic, but we don't choose some as some, let's say, almost every time you have your saturated liquid helium-2 bath, and you have some tank with you have to refill your saturated bath. We didn't do this. We have our saturated bath, which is directly connected to our refrigerator in a closed cycle. That means that you can work for days, weeks, months, exactly in the same value. And we are able to do this. Usually one campaign stands for, let's say, 1 month or so, because afterward all the teams are completely tired. But they work continuously, even during weekends, and we will be able to work with constant temperature of better than 0.1 milli-K. And we have a very huge statistic convergence, of course, and that has been used by different experimenters. And just before ending my talk, I will just say a few words about our ongoing measurements. We do now currently we do some measurement with visualization. So we have another cryostat here, where we have, let's say, it's an oscillating grid. So we have two grids, which is oscillating like this, and they are 170 millimeter apart. The size of the grid, they are square, and they are one side is, let's say, 110 millimeter. And they can oscillate in between 1 to 10 hertz, and the stroke is in between 1 millimeter to, let's say, 20 millimeter. And this is an experiment we done with Pancho de Ribard, with Jérôme Desplat, which is not there, and with our PhD student, which is the main investigator of this, which is Clément Brett. And okay, that's it. So we have two high-speed video camera with long-distance microscope or sometimes some lens to be able to see either some very small field of view, or we can increase it by just changing the objective, right? And here, this is the first preliminary result with 3D measurements, where we can have here the Lagrangian track. And this is 26 millimeter by 26 millimeter by 26 millimeter. And we use backlight illumination like this and like this. I didn't say this. So the camera is at 90 degrees. And this corresponds to 800 by 800 by 800 cubic pixel. So I hope we will be able to publish soon a result about this. So this is the conclusion of my talk. I hope you are now convinced that to reach ultra-high Reynolds number, you need to have liquid helium because of consumption power. And it's not only theoretical, but you have done it. And I'm sure that if you let us know what your dreams are, we may be able to do this, realize this together, as we do in the Shrek collaboration, which is involving so many people. And here I just show you one of our main results, which shows that we are being able to see that there is no difference between superfluid and normal helium as far as inertial range or even integral length scale is concerned, and that we are the same result for kinetic energy dissipation, injected and dissipated energy. So concerning other results, which have been done with micronic sensor, Olean sensor, just late on Thursday morning, I invite you to see the talk of Philippe and Pancho, which told you all about this. So I'm now just waiting for your question.